Okay, good morning everybody. Thank you for coming to this seminar. So I'm very happy and glad to introduce today and welcome Kumiko Kotera, our IEP colleague and deputy director. Kumiko is directrice de recherche au CNRS and well-recognized expert in high-energy astrophysics. Kumiko earned a lot of awards and distinctions, including the Young Star Awards in 2012 from the American Physical Society, but also the CNRS Bronze Medal, I think it was 2016, for your modeling of multi-messenger emission from a large variety of sources, astrophysical sources. Most importantly, Kumiko is a co-founder of the GRAND project and GRAND experiment, and spokesperson. Of course, I was very stressed, and of course I do it. I should be relaxed. Okay, yes. So, Kumiko is the spokesperson for the GRAND experiment, and you will talk about this experiment today, and I leave you the floor. Thank you for accepting our invitation.
Thank you so much, Clément. Can you hear me? Yes, okay. So thank you for this very nice introduction, Clément. Sorry for putting pressure on you. Somehow, I didn't, but somehow. Okay. And thank you very much for the invitation, and thank you for having me here today. Actually, it's quite moving to be here and to present my project to this place where I grew up. And I'm going to talk today, indeed, about GRAND, the giant radio array for neutrino detection, and how we could go towards EeV neutrino astronomy with that experiment. So EeV is actually 10 to the 18 electron volts, and so this is colossal energy. It's about more than 5 orders of magnitude above what the LHC can probe in terms of LNG for particles. So this is pretty huge, and these are particles that should be produced in the universe and that we would like to detect. Our final goal here is going to be to understand the most violent objects, violent events happening in the universe. So we have detected recently many types of new sources, many types of new transient powerful events, such as neutron star mergers, black hole mergers, magnetar flares, all these things that are extraordinarily powerful, but the working of these objects, in spite of some detections and multi-messenger detections, is not understood yet. Sorry, the working, their evolution, how they emit light and other messengers. These are things that we would like to understand. And in order to do this, we're going to have, so today we can and want to have a multi-messenger approach. So by multi-messenger, I mean that we're going to combine, obviously, photons in all wavelengths, but also gravitational wave signals, because all these sources are very compact and massive with asymmetries, so there should be copious emitters of gravitational waves. And then these sources have very powerful outflows that can accelerate particles that we call cosmic rays, charged particles, such as protons or heavier elements. And these cosmic rays, well, as they are accelerated inside the source or as they escape and propagate inside the intergalactic medium, can interact with various backgrounds, such as photon backgrounds, baryonic backgrounds. And they're going to produce secondary, very high energy particles, such as gamma rays or neutrinos. And in this picture, what's very interesting are neutrinos. So neutrinos are precious providers of information, because contrarily to cosmic rays, they are not deflected by magnetic fields because they're neutral. So for cosmic rays, when you have cosmic rays coming to Earth, you don't necessarily point back to their sources because they're deflected during their path, their flight from the sources to us. But for neutrinos, they come directly, so they can point back to the sources. Also, neutrinos have low cross-section with anything, so they can really let us see deep in objects. Also, we can probe far in the universe thanks to them. And they are also a clear hadronic acceleration signature, which is not the case of gamma rays, because gamma rays could be produced by leptonic acceleration, electrons and positrons. So neutrinos are very precious. Well, we also have gamma rays that we could detect, but gamma rays can be absorbed during their flight to the Earth due to the various photon backgrounds in the intergalactic medium. And so, yeah, with neutrinos, we can go very far. We're going to talk today about two types of neutrinos: cosmogenic neutrinos that are produced by ultra-high energy, by cosmic ray at the extreme energies during their flight from the sources to Earth in the intergalactic medium when they interact. So these are cosmogenic neutrinos. This barbaric term just means it's during propagation. Or astrophysical neutrinos that are produced at the source during the acceleration of these particles. So neutrinos have been detected over time over some range of energy, like EeV especially. And then lately, since 2013, we've been detecting up to PeV energy neutrinos, 10 to 15 energy electron volt neutrinos, thanks to a detector in Antarctica, which is called IceCube. But then above, at ultra high energies, so above this PeV energy, we have not detected any neutrinos, although we know that they exist. Why? Because these cosmogenic neutrinos should exist, because we do detect on Earth ultra-high energy cosmic rays at 10 to the 20 electron volts. These are routinely detected. And when you have interactions in the universe here, you take the secondary neutrino that is produced, so these interactions produce secondary neutrinos that take up 5% of the primary cosmic ray energy. So because we detect 10 to 20 electron volt ultra-high energy cosmic rays, we should have neutrinos showing up at 10 to the 18 electron volts. So these cosmogenic neutrinos are guaranteed to exist, okay? But we haven't detected them yet. And so the hunt for these cosmogenic neutrinos has been a thing that people have been talking about for many decades. But then the paradigm kind of changed over the last 5 years. So when we started this grand project and we wanted to detect, so what we really were selling were that indeed we wanted to detect these cosmogenic neutrinos, these diffuse flux of neutrinos coming from the universe, stemming from propagation of ultra-energy cosmic rays. But then there was this huge boom in multi-messenger astronomy and time domain astronomy. We started detecting gravitational waves, we started detecting gravitational waves with counterparts, and then we had also we had many of these possible coincident events between these PeV IceCube neutrinos and electromagnetic counterparts. So today, I think looking for a diffuse flux is not the thing that we want to do. It is interesting to try to catch this guaranteed cosmogenic neutrino flux, but what we would really like to do in order to be part of the game today, and the game today is multi-messenger astronomy at high energies, we need to detect point sources and find transient neutrino sources. And this is today the goal, I think, should be the goal of our community, I mean, my community. And this is what we endeavor to do with GRAND. And to do this, we need, obviously, an excellent sensitivity, but also, if we want to do astronomy, we need sub-degree angular resolution and a wide instantaneous field of view in order to catch these transients. So, yeah, the next generation detector has to combine, for neutrinos, has to combine all these characteristics. So then how do we move forward? So there have been many techniques that have been explored in order to detect these ultra-high-energy neutrinos. So the idea is that, so this is a very nice sketch that was made by Valentin and Simon. So you have neutrinos so neutrinos interact very little, so you have to take some good chunk of material to have them interact. So if you have a tau neutrino coming to the Earth, it can go through a piece of Earth, interact, produce a tau particle that can escape in the atmosphere, and then the lifetime of the tau is short enough that it will decay, and after this decay, the particles that are produced are going to interact with the molecules of the atmosphere, generate secondary particles, and these will interact again, etc. So you generate an air shower here that will develop in the atmosphere. And so this air shower can be either directly observed by particle detectors, these secondary particles, or you can detect them with via the light that this whole shower emits, with fluorescence telescopes, for example. And the same thing can also happen in ice. If you have particles, neutrinos going in ice, it can interact, produce an air shower, and this can also be seen. And another thing that happens, and which is really important here, is that we're going to generate a radio emission in this air shower, because the particles, the charged particles, in particular the electrons and the positrons, are going to be deflected by the magnetic field of the Earth and go one way and the other, and this will generate a current. And the moving current generates an electromagnetic field that is actually detectable in radio. So you have this radio emission that is produced either in ice or, although in ice it's not exactly the same system, but yeah, you have radio emission in air or in ice, and these can also be detected by these radio detectors. So you have experiments that already exist, some in green, and many of them that are upcoming in gray and yellow. And so you can see that there are indeed, the community is interested in that direction, and many projects are thought of with these different techniques. So the projected sensitivities of these different instruments is quite ambitious, actually. We all want to go deep enough, so this is the diffuse neutrino flux predictions in gray for, in particular, cosmogenic neutrinos, and we want to reach this low sensitivity, this high sensitivity that would allow us to almost guarantee the detection of cosmogenic neutrinos. This is for the diffuse flux, namely the flux that you get when you integrate over the whole sky. But again, what I'm mostly interested in are point sources. So if we look at one direction in the sky and we actually see a transient neutrino source. So here you have the fluence sensitivities. So these shaded areas are for different experiments, and this is to guide the line. This is a model prediction for a source of the type of GW170817, the gravitational waves and source that was the kilonova that was observed both in gravitational wave and electromagnetic counterpart. And this is a possible neutrino flux prediction from a given model. So yeah, if we get down here, which is the case of ground, for example, this shaded region in brown, we would have a chance to observe such a transient event in neutrinos. So why is angular resolution key for multi-messenger networks and to do this multi-messenger astronomy? Well, it's kind of obvious, I guess, but just let me say it. So in the future, so today we already have several associations happening between ice cube neutrinos and electromagnetic counterparts. And with other instruments that are going to be in place soon, LSST, Vera Rubin, SWAM, these instruments are going to detect so many transient sources that, and we're going to, so we will have many more false associations coming in. So we need to be able to skim interesting events and narrow down in particular the search area. We can be, and on the other way around as well, right? We cannot send an alert from neutrinos and say, okay, please, all the observatories there, look at this patch of 10 degrees in the sky. This is not really practical. So this is why we really need, as alert providers in terms of neutrinos, we need to have to really have a better angular resolution so that we can typically say, like, okay, please look at this 0.1 degree region in the sky, and then all these instruments that have a small field of view can also patch it a little bit or just point and go there. So this is quite crucial. And so if you look at the different angular resolutions of these upcoming projects or existing projects, what's quite interesting is that, so up here you have instruments that operate in ice, so the sketch that I showed earlier, where you have neutrinos coming from beneath, and but in the ice. And these instruments are very efficient because the radio emission in ice is pretty intense, actually. But in terms of angular resolution, the reconstruction is quite dire, and it might be quite tough. On the other hand, in-air radio experiments such as ground will do sub-degree angular resolution, and this is really our advantage for astronomy. So what I say usually is that we are complementary, and techniques are very different, so we should go for both. But yeah, I think this is absolutely crucial in the next, in the future of this field. We also need a wide instantaneous field of view, and what's very interesting is that, so for ground, typically, so this is the instantaneous field of view if we have several locations of several arrays of detectors of ground on the Earth, and each of these bands is it's a portion of sky that is seen by one detector. But yeah, what's very interesting is that although the instantaneous field of view of a given instrument like ground can be of just 6 degrees, as soon as you integrate over 24 hours, you get 80% of the sky. And then if you have more than one site, then you get to 100%. In the end, I mean, this is not just advocating for ground, but advocating for several sites, or several instruments. We need, in order to have a good chance of seeing transients, we do need at least the northern and southern hemisphere, which is very natural thing to say, but yeah, I would like to say it. And okay, so now I come to the core of this idea of ground. So we want to ground is a radio detection instrument. So again, you have tau neutrinos coming, interacting in the Earth, producing a tau particle, decaying, producing an air shower. The particles are deflected in one direction and the other due to the magnetic field of the Earth, generating this moving current, generating this electromagnetic signal around tens to hundreds of megahertz. And if you put antennas here on the slope of a mountain, typically, then you can detect this signal. Actually, this radio signal has already been detected with several instruments, and the radio detection technique of astroparticles is benchmarked. It is a mature technique. It has been used on Aera, LOFAR, Kodalema, Tunkarek Strand, and we do understand very well what we see here on the ground. Although, what has happened before is that we have measured cosmic rays coming from above. And these are vertical air showers that develop over 10 kilometers of atmosphere, and that leave footprints on the ground of about 400 meters. So this means that you need a dense detector in order to sample nicely the radio signal. Okay, but if you want to if you want to detect these very inclined air showers, and even for ultra-energy cosmic rays coming from inclined directions, these leave footprints on the ground of a few kilometers. So we can live with a sparse array and still have an excellent sampling of the signal. If you can build a sparse array, you can build a very large array. If you can build a very large array, you can go for very low fluxes, and this is exactly what is needed to hunt these ultra-high-energy neutrinos that are rare. So it seems like radio detection can be an excellent tool for ultra-high-energy neutrino detection. Also, to build large arrays, radio is great because radio antennas are, especially the way we want to build them, they can be very scalable, cheap, robust. And so all the ingredients seem to be united to make things work. So the grand concept is very bold. So we want to deploy 200,000 radio antennas over 200,000 kilometers square. So this is the size of England. So yes, it is bold. It's not going to be in one place. As I said, this wouldn't really make sense, even scientifically. And we're planning to actually, ultimately, we are thinking of having 20 subarrays of 10,000 antennas distributed over the world in favorable locations. So by favorable locations, I mean places where it is radio quiet, so desertic places usually with a good topography, so mountains to catch the neutrinos and a slope to catch the radio signal. And then you need easy access for installation and maintenance. And then actually, so we've done many campaigns of measurements in many places in the world, like China, Argentina. And these places exist, really. Like the world is very wide and vast, and these desertic places are really quite abundant, but what we bump into are political problems. And so this is the major, that's, I think, our possible stopper. And so far, and yeah, our main difficulty, as usual, I guess, technical things we can solve, but human problems, it's more difficult. And so yeah, today we are deploying in 2 places, in the northern hemisphere in China, in the Gansu province, here at the border, at the edge of the Gobi Desert. And here we also have a prototype at the Auger Observatory in Malargüe, in the Mendoza province, in Argentina. And this is going to be our first, our next step, actually, and maybe in the end we live with this, and we're trying to optimize everything so that maybe we don't have to go to such a huge subarray deployment, number of subarray deployment. We might just go for, I don't know, 2-4 sites, and at least the major 2 big sites are going to be China and likely Argentina. So I already showed this in a broader context with other experiments, but yeah, the simulated performances for ground are very promising. So we will be capable of having a good sensitivity that will allow us to almost guarantee the detection of cosmogenic neutrinos for the most standard scenarios of sources of ultra-energy particles. And yeah, we will have an excellent also sensitivity for transient sources, and most of all, we will have an excellent angular resolution. This is the work of Valentin de Koon. But yeah, this is, again, this sub-degree 0.1 and even better angular resolution is our key advantage. And with this setup, what we want to do is to embrace a very rich science case. So I've already talked about the ultra-high energy neutrino science case, astronomy and cosmogenic neutrino flux hunting, but also we can do ultra-high energy cosmic ray physics, hadronic physics, neutrino physics, ultra-high energy gamma ray physics, and even radio astronomy in a novel way, because we'll have these huge radio antennas that can have a look at half of the sky at a given instant, and if you just integrate all the signal from the various antennas in an unphased way, you can actually have a very good monitoring of what's going on in terms of transient radio events, such as fast radio bursts. So this could be a very good science case as well. So we're not going to build the 200,000 antennas tomorrow. We're going step by step. And today we're working on this prototyping phase where we're going to demonstrate the technique of detection and of reconstruction with cosmic rays. And I'm going to talk about this later, but then we're going to develop from 2025, do the R&D for the next phase and deploy these two big arrays in the northern and southern hemispheres. And then once this is done, and we know how to build a large subarray, then we freeze the design, we give it to industry, and then we duplicate this subarrays over the world so that we get a detector that is sensitive enough to really do neutrino astronomy. So that's the goal. We will face, and we are faced, I mean, GRAND has to overcome several technical challenges. Two major challenges are, first, to do autonomous triggering on radio signals, and this is a thing that the community has been working on for decades. The idea is that so far, all the radio experiments that I've talked about have been detecting air showers, so cosmic ray showers, using a secondary instrument, a secondary trigger. They have like scintillators, water tanks that can detect the secondary particles coming from the showers. They know that the shower has arrived, so they go look in the radio data, and they see that there is indeed a radio signal, they reconstruct it, and it works very nicely. But this is not sustainable. You cannot build 200,000 radio antennas and 200,000 water tanks. This is exactly what we're not going after, because water tanks are very complicated. And so we want to just be able to recognize a radio signal alone when it has arrived. And to do this, it's quite complicated, because wherever you go, even in the most remote desert, in the Gobi Desert, the Pampa, in Argentina, anywhere, you're always very dominated by human noise. And this can come from anywhere, your car, road, even some things that are tens of kilometers away. And it's very difficult, because it's not like light that you see. Actually, the radio waves are just very, pernicious. And so yeah, you really need to go have a measurement to see that the environment is quite clear. But even when you have a clear environment, you still have lots of these transient radio noise that come in. And so you need to be able to discriminate this. And to do this, also, and not just discriminate, you need to have an equipment, a data acquisition system that is capable of actually to be alive whenever all these transient events, to be able to swallow all these transient events. So we need to build something that can actually demonstrate this autonomous triggering. This trend experiment built by Olivier Martineau was quite a very good precursor that showed that this should be possible. But today we're building 3 prototypes: Grand at Nançay, Grand at Auger, and Grand Proto 300, in order to test this. The other thing is that we want to show that with these very inclined air showers and the signal that you get on the ground, we're able to reconstruct the parameters of the primary particle. And this is not a given, because we do understand what's going on when these showers fall vertically, But the physics is extremely different when you incline everything, because you have asymmetries in the atmosphere, you have reflection from the ground. I mean, you have tons of other problems that make it very difficult. And very few people have done it so far. I mean, almost when we started, it was almost a no man's land. So we also need to work on this reconstruction of very inclined air showers. And these are things that at IAP we're really involved in, and that the Grand France team is very much involved in. So we're going to work on conventional methods, but also machine learning methods that we are working on. Another challenge that you might be wondering about, and that everybody asks me usually, is how is like more almost philosophical, but it's not, it's technical. So how are you going to run a giant array? How are you going to deploy and run 200,000 units over 200,000 kilometers square? How much will it cost? Who will pay for it? And these are questions that I'm usually asked. So yeah, we have time to solve these technical problems because we're not there yet. But the answer that we give and that we believe in is that at some point we have to go industrial. We can't be just building this with a physicist approach. It's just not the same scale. So what we want to do, as I said, is that at some point we freeze the design when we have a large array working, 10,000 antennas. We know that how the antennas communicate. We know the volume of data. And then we build the constraints that we want. We give everything to industry, and they deal with it. Because, like, if we have cables, connectors, and everything, this is bound to fail at some point, and we cannot maintain 200,000 cables and connectors. But if we have, like, for example, ASIC chips, things that are very simple, very robust, you think of, yeah, building things, deploying things and building things large scale is something that humans are capable of with industry. You think of the GSM antennas, you think of electric poles. I mean, they're everywhere and at with very large volumes. So it is possible. It's just that we cannot just do this with 400 physicists. We need to do this properly industrially. So that's my answer to this. But okay, how much time do I have left? Okay, so today, so it's a very exciting time, and this is why I'm so happy to be able to give this talk today. So we're just taking a turn with Grand, because we are finally taking data after this long COVID period, which was very frustrating. So we have started to deploy this year, in 2023, our first antennas. So our antennas look like this. So it's a butterfly antenna with on top of a 3.5 meter pole with a low noise amplifier here, Wi-Fi, bullet Wi-Fi here. Here you have a solar panel that constitutes a lid for a box here that contains the battery, charge controller, the data acquisition system, and the electronics, look like this, with a filtering over 50 to 200 megahertz. And so we've been deploying 13 antennas in China, 4 antennas in Nançay, and 10 in Auger. So the first 13 antennas in China are the beginning of this of a 300 antenna prototype that we're going to deploy. But yeah, we're still in this commissioning phase and validation phase. At Nançay, where you know where it is, Nançay is 2 hours south of Paris, and there is this large radio telescope that you probably know of. So we have these antennas in the woods that we've deployed in order to test. So so you can see here a spectrum of the radio environment here, that you can see that it's we had to filter out the FM band. So it's not an ideal environment, but it still serves to be a test bench for a place, to work on hardware. And we can test things and not go to the other side of the world. So it is a good place for all the Europeans that work on ground to test, in particular, the triggering, and yeah, lots of details on the hardware. Then we have Grand Auger, and Grand Auger is quite important here at IAP because you can see the signature here. So it's an international prototyping effort that gathered in particular 5 institutes here, and it is a setup that is hosted at the Auger Observatory. The Auger Observatory is an ultra-high energy cosmic ray detector that has been operating since 2007, 6, 7. And so we benefited from the structure of these, of the AERA antennas. So they also have this a radio detector there, and they lent us some of these structures. So you can see here Olivier and Fred Magnard working on dismantling one of the AERA structure and putting a ground antenna on top. So this is what it looks like in the end. Actually, Grand Auger is indeed very anchored at IAP because we also funded and installed really and made the central data acquisition system of this this setup. So Fred made it, and yeah, there were several campaigns. I was there like a month ago, and yeah, so the first data is still in commissioning phase. Lots of things we don't understand, obviously, but they're nice things. We have some, we see some pulses. So this is the amplitude of radio signal as a function of time. This is the power spectrum density. You can see that there is a FM band. You can see some beacon that are transmitted for calibration. You can see TV carriers, and we expect in the end about 4 to 7 events per day. And here you have a time frequency, the time frequency phase space. These are the frequencies. This is the FM band that you see here, and this is the time. So you can. What's interesting is that you can see the days here that show up, and well, I don't think here. I think here it's more related to the battery noise. Or the charge controller noise, but we're working on cleaning this up, and then it would be nice that we see this, but that it's the galactic noise actually, which should also vary. Now in China we've deployed 13 antennas, but the plan is to really have a big prototype, Grand Proto 300, so in Shaodushan. So Shaodushan this is China, okay? You have to fly to Dunhuan, which is a very nice historic place on the Silk Corridor. And from Dunhuan you have to travel like 3 hours to get to this very remote place, Shaodushan, which means small mountain. And there we're going to deploy 217 antennas that will collect about 90 events per day. 90 events are cosmic rays. And the idea is that we measure cosmic rays in this spectral range for cosmic rays. These are cosmic ray measurements by other experiments. And this is a very interesting region where we have galactic sources of cosmic rays ending and extragalactic cosmic ray sources taking over. So it's a messy region that we don't really understand. So we're going to hopefully do a bit of physics here too, with this setup. So this Grand Proto 300 will be a real validation test bench for triggering and for reconstruction. And yeah, so we have deployed these 13 antennas. We're in commissioning phase, and you can see here that we are in a much better place here in Shaodushan. Don't look at the yellow line, which is a channel that is very noisy, but if you look at which points to the up to the sky, but what we want is to really look at the horizon. And these north, south, and east, west channels, red and blue, are very quiet. You don't see any FM band, you don't see anything. It's extremely clean. We also see some coincident pulses, namely in the various arms of the antennas, we actually see something that is a pulse that's coming, which is very good. And so we're working on this. This again here you can see Olivier and Fred. And so yeah, the next steps are going to be to understand what's going on in our antennas, and then we deploy The next 80 antennas that are already in our storage room in China, and we validate the ground detection principle up to 2025. So this is really happening this year. It's completely taken off, and yeah, so it's extremely exciting time. Just, I wanted to give you a heads up, 5 minutes, yeah? Okay, on what we are really doing here at IEP technically. So just so you understand better, again, the frequency range of ground will be 50 to 200 megahertz. We have pulses that we're hoping to detect. So this is a real physical cosmic ray pulse. So you have pulses that last less than 100 nanoseconds like this, and you have galactic noise here that we have to go above in order to have a detection, and that's what we're looking for. So if we go 3 to 5 sigma above this line, that's when we say that we have that when we trigger at antenna level, and then if we have this at 5 stations, that's when we say that we might have an event. And so that's the second level trigger. And this is the footprint that you get on the ground with many antennas, so of the radio signal. And this is really interesting because you have this nice ring that is made here at quite high frequencies. And it results from the fact that when the air shower develops, the radio signal is emitted at different places in this air shower, and because so it's emitted to the ground, and because the refraction index of air is not 1, then you have delays of this light reaching the ground. So it's this Cherenkov effect that there are delays, and there is a place, an angle, sorry, an observation angle where you have an accumulation of signals of radiation that were emitted at different places in the air shower. So this is called the Cherenkov ring, and it's an excellent tool to do reconstruction, because if you can measure something like this, you can get the shower core, and then you can get the direction, then you can get all other information. And this is one thing that we have been pretty much involved in here at IEP, and more generally in Grand France with all these people here. So this is a slide, I think, that I stole from you, Valentin. So what we're doing first is that we're measuring the time. So when we get a signal, we can measure the time of arrival of this signal at different antennas. And if you can fit, say, a spherical wave front shape to this timing, you can reconstruct already so you can get a first reconstruction of the parameters of the air shower, and then you can add this ring effect that I mentioned earlier. So you look at the lateral distribution of the signal here by cutting here the plane in the plane of the shower, and then you get more information, and you can very nicely reconstruct the arrival direction to sub-degree angular resolution. But also not just the shower, the arrival direction, but also the an estimator of the nature of the particle and also the energy. So this is a major effort. Another effort. So in order to understand this reconstruction, we also want to understand the physics going on in these air shower, these very inclined air showers. As I said, this is well understood. This is not. In particular, so this I think you saw, many of you saw with Simon Chich's thesis, but basically the idea is that by inclining the air shower, your shower develops in a much less dense atmosphere than the vertical ones, and it means that you have less collisions, and the effect of the magnetic field of the Earth is more intense. If this is the case, we're going to have particles being more deflected, and if you deflect more the air shower in the shower front, you're going to lose coherence. And you're going to lose coherence, and you might also have more synchrotron effect due to the magnetic field. And this is what you can see here, that actually if you compare the lengths, characteristic lengths of coherence and radiation, I mean, in collisions. You can, you see a place, so here, these are less inclined showers, more inclined showers, less denser atmosphere, less dense atmosphere. And so as you go to more inclined showers, you're actually going to be more incoherent, so you're going to lose signal, and you're going to introduce also a synchrotron contribution. And this is something that we also see in, so yeah, in the particles, you can really see this spread in the, so these are vertical showers seen from above. You can see that the particles are very symmetrically distributed, and if you incline the showers, you get an effect from the deflection of the magnetic field, and the shower is spread, and you lose coherence. So yeah, these are things that that can also be seen in simulation. You see a signal cut off at very inclined showers. For very inclined showers, we see some patterns that are reminiscent of synchrotron emission. So these are things that have been done by, and that are being done by the students in our group, PhD student Simon, who graduated already, but then also Marion, who's here. We work also on layout optimization. So this is what, like, how do we put our antennas on the ground in a hexagonal, triangular pattern. So this is a study that we really worked on, and that is actually being implemented in a Grand Proto 300 layout. We found in particular that it's more productive and efficient to put an infill structure like this with, if we have like spare antennas, it's more intelligent to have a coarse array here and have an infill array in the center to gain sensitivity at low energies. And then we're working also on the trigger, which is, as I said, how to say that, when and how to say that we have detected an event. So at different levels, at the unit antenna level, or at array level, using the information of different antennas. And this is absolutely necessary to reduce the volume and to be able to cope with all the transient events that are flooding us. So this is an effort that is being done together with Karlsruhe, with KIT. So yeah, I'm not going to detail this, but yeah, this is fundamental for the next phase of GRAND, and will be tested on the current prototypes. So GRAND today is about 100 collaborators from 12 countries, with a MOU that has been signed by 13 parties. So you have 3 French institutes, IAP, LPNHE and LUPM, and more to come. We are on the roadmap of several European institutes, in particular APEC, which is the Astroparticle Physics European Community Consortium. We're also in the European Strategy of Particle Physics Roadmap, the CNRS perspective of Institut. And yeah, so Grand France, just to summarize, this was yesterday, and I think you can see many faces here that you might recognize. Claire Guépin was a student here, and she's in Montpellier now. Matthias Tueros has been here as a on sabbatical, actually during COVID, so you might have not seen him too much. Simon, so this is Olivier, Marion, Valentin, and Anastasia here as well, who's here today. And so, yeah, we are obviously very involved, because Olivier and I really founded this project, as Clément said, here at IEP, which is, yeah, so here in the forum. And yeah, so we are obviously involved in all the decisional processes of GRAND, but also pillars of this science and data analysis pipeline. And also involved in the collaboration life. Here we have contributions also from various people, including Fred Magnard, but also people that you might know of, Jean-Marc Collet, François Legrand, who are really working on the data management aspects and so on. So yeah, it's an effort that is very much supported and quite visible, I think, in France. I've reached the end of my talk, so here are some references that I invite you to look at, in particular, this very nice documentary that Jean made, which is very beautiful and contemplative, and maybe it helps you want to join GRAND at some point and join the effort. Thank you.
Thank you very much, Kumiko. It's fine, we will see. So people on Zoom can post questions if they want. Is there any question in the room?
Thanks a lot, Kumiko, for this very nice overview. I have a very naive question, because at the beginning, from what I understood, you said that the main target of GRAND are cosmogenic neutrinos, and then you focused on transient sources. So are the neutrinos that you've been talking about, neutrinos emitted directly by the source, or during propagation? I didn't get this point.
So, yeah, the main target of GRAND used to be cosmogenic neutrinos. This is how we started, but this was 2013, 14.
Okay.
And then gravitational waves were detected and everything. I mean, the whole scenery changed. And today we have the main target of GRAND is to do multi-messenger astronomy and ultra-high energy neutrino astronomy, and to detect the neutrinos from the sources.
Okay. No,
from the sources.
Okay.
And yeah, what I meant was that we have the means to actually do it.
Okay, so there are neutrinos emitted directly
in the source.
In the source. Okay.
Yeah.
Thanks.
Thank you, Kumiko. That was very nice. There was something I didn't understand in your technical discussion about the difficulty of measuring these grazing incidence showers. Because of its grazing incidence, you know, the neutrinos are coming often from below, okay? The taus will continue roughly in the same direction, and then the showers from the tau, you know, some of them will come down, those are the ones you will detect, and some of them will keep going up. But I would think that the height at which the ones that come down will be lower than the showers that are from other sources that come almost vertically. But you said the opposite, so I was confused.
So, sorry, what are the particles, wait, the ones that you're talking about that come from, I'm not sure I got your
So
point.
what I'm saying is that to be sure that it's a neutrino, you prefer it to come from below, because nothing else can come from below except a neutrino.
Okay, that's true, yeah.
So you have these tau neutrinos that go into taus, and then in this diagram here, one has the impression that the air shower is coming from below, so at a high density, whereas the ultra high energy ones, they come from higher and they go through a variety of densities. But what I thought you were explaining in the slide towards the end was the opposite effect.
Yeah, sorry. Actually, yes, indeed. It can be confusing, yes, indeed. Actually, here it's about cosmic rays, indeed. So this study here is for air showers of cosmic rays, and indeed, everything I said after is about the incoherence and all these things are for cosmic ray air showers. Actually, it's very good for us because it means that it kills the signal of cosmic rays. So these very inclined air showers coming from above are going to have to emit incoherently. Not just, but yeah, the signal is going to be killed. These are for cosmic rays again, right? And for neutrinos, it won't work this way because, as you said, exactly, they come from below, so they develop in a dense atmosphere, so they will still emit strongly. So it's a very good way to kill background for us, for neutrino research. For those doing ultra-high-energy cosmic rays, not cool. But then you have to actually choose a good site where the magnetic field is actually less intense, and then you still get to see, this is what you see here, you still get, at the Auger site, typically it's interesting because the magnetic field is less strong, and then you have, you don't have this cut effect because there is no such big incoherence effect kicking in. So if you choose well your site, you can detect either neutrinos or cosmic rays.
Thank you very much for very interesting talk. I wanted to know how do you compare the resolution or the possibility of distinguishing between different types of primaries with this radio method with respect to, for instance, Cherenkov telescopes or direct detection on the ground. Because here, the radio is much, let's say, secondary emission than in the case of, for instance, Cherenkov, which is directly comes from mostly from the primary.
So indeed, we right now I think we have a hard time discriminating between gamma rays and cosmic rays, for example, if we take our prototype. So indeed, with Grand Proto 300, we would love to actually be able to do ultra-high energy gamma ray astrophysics. But in order to do this very relevantly, the best thing would be to have a secondary detector like scintillators or something like this that enable us to discriminate, to veto, indeed, because we only measure the electromagnetic component, and yes, we would need the muon information or the supplementary information. But yeah, the discrimination between cosmic rays and neutrinos, as Gary said, actually it's very easy because we have an excellent resolution. We can just say that everything coming from below is neutrinos and from above are cosmic rays. So on this we're safe. Gamma rays and cosmic rays, more complicated. But we have, we also are in pretty good shape to measure the X-max, which is an estimator of the composition. And this might help us to,
Thank you, Kumiko. So I have two questions. One question is because I know very little about this subject. So of course they tell us about sources, and I can see that is quite important. But what about physics? I mean, can we use them to learn new physics, high energy cosmic rays?
Definitely. So I'm not that well versed in that aspect of the science case, but indeed we can measure we can do neutrino physics, because we're going to, if we do measure neutrinos at ultra high energies, we have no information so far on the cross-section evolution at these energies, so this is going to be a big thing. If we measure flavor, we can by measuring the tau neutrinos, we can have information on the flavors of the neutrinos and then on the oscillation and such. So, yes, definitely we can do neutrino physics. We can also do hadronic physics, and this is already at the stage of Grand Proto 300 of a prototype. We can, so for this, to do this really very nicely, again, we would need a secondary detector, which is still on the table, actually. So if we had a way to get the muon content of the showers, for example, we could measure. There is this big thing going on in hadronic physics around this energy, 10 to the 18 electron volts, about what's called the muon discrepancy. So the Auger observatory is seeing that there are more muons than is expected from physics, from the standard models derived from the LHC. So these are things that we could definitely probe.
Thank you. And my second question is related to all these other radio astronomy experiments that are going on. You know, you referred to Nançay, but there is, for example, SKA. Are you have any interaction with them? Can you use what they are using, they are doing? What's the link between what you want to do and what they are doing?
Yeah, it's a very good question. So SKA is a radio astronomy facility, right? And it's extremely dense and much smaller in surface. So we couldn't do what we're doing with SKA, although there are indeed synergies. There is a cosmic ray section, a science case in SKA. And by the way, part of the funding that we get from China is SKA China. So there is clearly a link. And I think to study air shower physics and radio physics, we have definitely collaborations, but SKA is not designed really to hunt for the ultra-energy neutrinos. But yeah, we can. And there is also Nénuphar, which is a precursor of SKA, which is in Nançay, on which Valentin is working as well. And there we also have synergies. We're working together with Philippe Zarka, also on this radio astronomy topic. So we are, yes, we are a community communicating indeed, collaborating.
Okay, two questions. What if now I'm thinking of the source and I'm building a source model, what is the unique information the neutrino brings me in terms of lifting model degeneracies? I mean, the physical information, what is it that I get?
So one first answer is, you understand that there is cosmic ray acceleration there, because it's a hadronic signature. We get the energy, we get the power of the source, part of the power of the source, because there are very stringent constraints to actually get to 10 to the 18 electron volts, which means that ultra-energy cosmic rays get to 10 to the 20 electron volts. So this really means a lot about the budget, energy budget of the source. So you actually get an insight on the outflow, the plasma that's really accelerating these particles. So this is, I think, pretty unique already. Do you want me to elaborate, or?
No, I think that's clearly one of the things that I'm sure we'll be eager to know a bit better about the source physics. Anyway, I had a simple question, which is, what kind of data volumes are we talking about in terms of not collecting, because so many things are done on site, but suppose, there is a data center somewhere in the world. What are we talking about? Is it gigantic, or it's actually a small amount of data and most of it is in terms of the processing that needs to be done? So is this actually pushing the envelope anyway in terms of data volume or data complexity, or actually no, the thing is actually getting the data? Can you elaborate a bit more?
Yeah, so I think we're much less voluminous than Vera Rubin. But
well,
we're talking here,
for you.
Yeah, yes, but we're still talking about over 5 years of Grand Proto 300. It's like 15 petabyte, about that. So, but this is the prototype, right?
And
it's 300. It's 300 antennas, but it's still raw data. So we are not. We're recording everything because we want to work on our methods. But then we have to clean things up because we cannot do the same and scale it up to 200,000 antennas. And at this level, so yeah, the flow, at least, of data I can show you is of order. So we're talking here about the target of this project we're working on is to go to, typically 1.5 kilobyte per second per unit. So you multiply this by 200,000.
Yeah, but that doesn't give me the answer. I'm thinking a data center.
So yeah.
I mean, then you have to have the simulations, and you have all kinds of things. So what is the sort of typical dimensions? Is this something at the size of an institute? Or this is like, IN2P3 data center stuff?
I think it can be IN2P3 data center stuff.
Okay, so that's sizable.
Yeah, it is sizable. It's not, again, it's not Vera Rubin. And today, by the way, we're hosted at CC.
A lot of CPU needed, or it's actually not the issue? It's more being smart in terms of analyzing.
Right now, it's more about being smart.
Okay, so that's the kind of thing where we can compete. Thanks.
A very last, very quick question.
Going back to what we were discussing before, so that the original goal of GRAND was these cosmogenic neutrinos. So which is the information that one can get looking at this? I think that is a diffuse background, right?
The cosmogenic ones?
Yeah.
So it's it's difficult, and this is why I think we have to move to source hunting. But from cosmogenic, by looking at the shape of the spectrum, by looking at the level already of the flux that you're getting, you can rule out many source models, or the composition of the particle. The composition of. So the cosmogenic neutrinos will give us information about the sources of ultra-high energy cosmic rays, right? Mm-hmm. So this means information on the population, the type of the density of population, the information also on the particle maximum energy acceleration, the particle composition, whether it's a proton or heavy element, the source evolution in time. Like if you had more sources in the past, you can actually, because neutrinos travel from z equals 11, or if you had more sources in the past, you have a higher flux. So, yeah, if you have a low flux, it actually means that the source evolution is not that good. I mean, that huge, that there were not so many. It's I don't know, SFR, star formation rate type evolution, or worse. These information we can get from the level of flux, and then from the shape of the spectrum. This is a more refined thing. Then you can infer. You can start discriminating between different populations of sources that predict different peaks, for example, also, or different cutoff. But it's a difficult game to me, very difficult.
Okay, thank you.
Thank you for this very interesting discussion. So if you want to continue this discussion, please don't hesitate to come. And let's thank again Kumiko.